Lecture 8, Part 2, Non-Uniform Circular Motion. Non-uniform circular motion means the speed is changing. If speed is changing, there's an acceleration with or against the motion. The acceleration is also perpendicular to the motion if it's going in a curve. So the acceleration has two components, a component with or anti-parallel to the motion to speed it up or slow it down, and acceleration perpendicular to the motion, involved with the motion's change of direction. This acceleration has two components, a tangential acceleration involved with speeding up or slowing down, and a centripetal or radial direction of the acceleration. As we saw in Lecture 8, Part 1, the tangential acceleration is related to the angular acceleration alpha times the radius. An example of non-uniform motion is a golf swing. Here is a golf club, swung from an angle from the vertical. As the golf club is swinging, it's going from rest to a maximum speed at the lowest point. Thus, the golf club is exhibiting non-uniform curved or circular motion. It's increasing its swing. The angular velocity omega is increasing from nothing to something. These are the tangential velocities growing. The speed increase is only in the direction along the arc of the swing. There is no movement along the shaft, i.e. no radial velocity v in the radial direction vr equals 0. Only a change in the tangential velocity, delta vt. It's speeding up. That means there is an acceleration in that direction, a tangential acceleration. The acceleration is less. It's greatest at the beginning and least towards the end. The tangential acceleration is coming from the force of gravity. The force of gravity in the direction of the swing is greatest when the golf club is raised at the initial angle, and the tangential acceleration is 0 at the lowest point. It is not speeding up or slowing down at the lowest point. And the cause of that acceleration, gravity, is perpendicular to the motion, so there is no contribution to the tangential acceleration from gravity at the lowest point. There is, however, radial acceleration throughout because the object is being moved in a curve. This is the acceleration involved with the golf club changing direction. This is our v squared over r relationship for the radial or centripetal acceleration. The radial or centripetal acceleration is the greatest at the lowest point, and the tangential acceleration is 0, the least at the lowest point. Why is the radial acceleration the greatest? It's because the radial acceleration, centripetal acceleration, is related to v squared over r. The velocity is greatest at the lowest point, so v squared over r means the centripetal or radial acceleration is greatest at the lowest point. The greatest directional acceleration, the radial centripetal acceleration, is needed when the object is moving the fastest at the lowest point. It's moving the fastest, so it's no longer speeding up or slowing down at the lowest point, so the tangential acceleration is once again 0. These are the components of the overall acceleration. Roller coaster physics. Here a roller coaster car is going around the loop. The car's forces, the forces on the car are the gravitational force and the force of the track are the normal force. Let's look at that again. Gravity is always pointing down or towards the center of the Earth, and the normal force is pointing normal to the direction of the surface of the track. These forces can combine or be in opposition to give us a net force towards the center of the curve. A roller coaster car goes through a vertical loop at a constant speed. For instance, A through E Rank the order of the centripetal acceleration, normal force, and apparent weight. Well, we have a car going around a loop on a roller coaster, as we just saw. Our only two forces are the earth pulling it down, the car's weight, and the track pushing against the car to prevent the car from going in a straight line through the track. The normal force, the force of the surface on the force of the track on the car, is what keeps it going in a curve. The centripetal acceleration, by Newton's second law, is due to the net force, which is in the centripetal, the radial direction. Centripetal acceleration means the acceleration towards the center, along the radius. The net force, the radial centripetal net force, is the net force from the normal force, the force of the track, and the weight pointing has to be towards the direction of the center of the curve, the centripetal or radial direction. We know that the centripetal acceleration, the radial acceleration, is related to the tangential velocity v squared divided by the radius. But we are told the speed is constant. So for the circle, the radius doesn't change, and the speed in this case doesn't change. So a constant v and a constant r means we have a constant centripetal acceleration, or radial acceleration. Thus, a constant, by Newton's second law, net force. A constant net force of the same magnitude pointing in the radial centripetal direction. Thus, they all have the same value of the centripetal acceleration. Part 2, what about the normal force? Let's look at the forces on this car again. There's the weight pulling down, and there's the force of the track perpendicular or normal to the surface. These are the only two forces on this car. We're ignoring friction. Thus, our net force, which must point in the centripetal or radial direction, is mostly caused by the force of the track, the normal force. When the car reaches position C at the top, the weight again pulls the car down. The normal force is in that direction, normal to the track, which is again pointing towards the center of the curve. The combination of the weight and the normal force is giving us the net force. The net force has to point towards the center of the curve for that to make a curve. But in this case, the weight is pointing in the same direction as the net force. So the normal force doesn't have to be as large, because the weight plus the normal force, in this case, at the top, is pointing towards the center of the curve. The net force, in fact, can be entirely made up of the weight, and no normal force would be needed. This would be the minimum speed. So what is the value? How do we determine the net force? And how do we determine the normal force? Well, we see the normal force decreases as the car goes from A to B to C. Again, the weight, the component, the force of the weight pointing straight down in position C is pointing in the direction of the net force. So the net force can be mostly made up of the weight and not as much of the normal force. Whereas towards the bottom, the normal force can do most of the contribution in the direction towards the center of the net force. So the normal force shrinks going from A to B to C because it needs less of a contribution towards the net force, because the weight is then pointing in the direction going from A to B to C more so and entirely at the top in the direction of the net force, so the track doesn't have to push as hard. By symmetry, A equals E, B equals D, and since the normal force is greatest at A, it is greatest at A and E. The normal force is less at B, which is the same at D. The normal force is the least when the weight is pointing in the same direction as the normal force at the top at C. The apparent weight is from the normal force. You feel heavy in your seat as the seat pushes up or the track pushes up on the car, pushing up on the seat. So the normal force and the apparent weight are the same. Next, finding maximum and minimum speeds for objects in circular or curved motion. First, find the minimum speeds for roller coasters, balls on strings, and even things in orbit. Well, back to a roller coaster car. Let's say the car is going around the circular track, but the speed is changing, getting reduced as it goes to a higher position. Going from A to B, the speed is dropping up to C. What minimum speed would it need to make it across so it doesn't fall and doesn't have any extra speed at point C? Well, we know the centripetal acceleration, the radial acceleration, is v squared over r. So the minimum speed, the smallest value of v for the same radius, will give us the minimum acceleration. By Newton's second law, times the mass by the acceleration, this gives us mv squared over r. The smallest v gives us the smallest a, which gives us the smallest value of ma, which is by Newton's second law, the smallest value of the net force. What is the net force made up of? There are only two forces, the weight and the normal force. The speed is the least at the top at position C. So the net force is the least at position C. The weight is pointing in the direction of the net force. And when the net force is the smallest, it is the same as the weight. The normal force is gone. The net force is the smallest amount. The net force is equal to weight plus normal. The smallest value of the net force is just equal to the weight. The net force is mv squared over r. Thus, the net force equaling the weight is the smallest value of the net force relating to the smallest acceleration relating to the smallest velocity, the minimum speed to make it across. The minimum speed to make it across is at the top. The weight alone serves as the force needed for the car to make it through the loop. Any greater speed than the car pushes on the track, and the track pushes back on the car to keep the car at any greater speed moving around the loop. So the weight is equal to the net force, and weight is equal to mg. So mg is equal to the net force, which is mv squared over r. Canceling out the masses, we have gravitational acceleration is equals v squared over r. Thus, solving for the minimum speed, v min is equal to the square root of g times r. This is a general result for roller coasters, for balls on a string, where the string, rather than the normal force, the tension of the string, is acting the same as the normal force in this situation with a roller coaster. A ball moving around on a string in a vertical motion will follow the same principles just discussed. And so will an object in orbit about the Earth, or about any object. Another example is walking. When you walk, your leg, not running, but when you walk, your leg is roughly acting like the radius of a curve in the examples we were just discussing, and your overall center of mass, which is pretty much at your hips, is acting like the same as a ball on a string, or the mass of a car, or the roller coaster car in the previous examples. Looking at the figure, the dot represents our center of mass, her foot placed on the ground. As she's walking, we see her center of mass goes up and down as she walks. The center of mass points towards the connection line between the center of mass and her foot is the same as the radius of the curve that her center of mass makes as she goes up and down as she walks. What's pulling on her center of mass? The force of the earth, her weight. What's pushing up on her? The floor, the surface pushing up on her perpendicular to her foot, the normal force. The normal force and the weight are in competition. But the normal force cannot equal the weight. Otherwise, the net force would be zero, and the velocity would be constant, same speed, same direction. But her mass is going in a curve. It's changing direction, so there must be a net force pointing towards the center of the curve, a net force pointing towards her foot. So the normal force must be less than her weight, so that the weight is greater than the normal force, causing the net force to be pointing in the direction of her weight, towards her foot, so that our center of mass follows a curve. Net force for any curved motion is mv squared over r. Net force is weight plus the normal force. But the maximum walking speed is the greatest net force. The value of the net force is the greatest when the normal force isn't present to cancel out the weight. When the net force is equal to the weight, that's the greatest maximum value the net force can be. The maximum value of the net force is the maximum, relates to the maximum speed. So the maximum walking speed is the maximum net force, which is equal to the weight with no normal force. Weight is mg, so mg equals mv squared over r. Cancel the masses, and we get the maximum speed is equal to, once again, the square root of g times r. A car going over a bump, the mass of the car follows a curve. If the bump, the hill, is a circle, the mass of the car follows a circular motion, just as the center of mass in the lady's hips followed a curved or circular motion from her foot to her hip. This is the same principle, a car going over a circular hill. A car of a mass goes over a hill at a speed. The shape of the hill is approximately circular, with the radius, as in the figure at the right. When the car is at the highest point of the hill, what is the force of gravity on the car? Well, the force of gravity is simply the weight equals mg. In this case, the mass of 1500 times gravity, so about 1500 newtons. What is the normal force of the road on the car at this point? Let's look at our forces. Weight is pulling down. Normal force is pointing up. But we know the net force must be towards the center of the curve. In order for this object to change direction to follow a curve, the net force must be pointing in the centripetal, the radial direction. The net force must point in the direction of the weight towards the center of the curve. The normal force must be less than the weight for there to be a net force down, for there to be a net force towards the center of the curve. If the normal force equaled the weight, then there would be no net force, and the object would go in a straight line rather than a curve. So the net force is, by definition, normal plus weight. If we're looking for the normal force at any time, it's an F net minus the weight. F net is mv squared over r minus mg. Plugging in our given values, we can solve for the normal force. What is the maximum speed the car can go over the hill while always staying on the hill? Of course, the car can go faster and leave the curve and fly over the hill, but the maximum speed to stay means the normal force is going to be present. As the car goes faster and faster, the normal force shrinks, and greater net force is needed for the car to make the curve, to stay on the hill. The maximum speed will be the maximum net force. How big can that net force be? The net force can only be as big as the weight. The normal force only decreases the net force. As the normal force decreases, the net force increases. And the maximum the net force can be is when there is no normal force. The net force becomes the weight. Thus, we return to the same situation. The net force equaling the weight, mv squared over r equaling mg. And again, the Vmax is equal to g times r, just as it was for a walking pace. Here we see a car on a level horizontal plane making a curve. As the car changes direction to turn to make this curve, the vertical forces, the normal force and the weight, in this case are balanced. The net force vertical is zero. There is no vertical force. There is no vertical net force. The car is not increasing or decreasing its speed or it's changing its direction vertically. But it is turning horizontally. So there has to be a net force towards the center of the turn, to the center of the curve that is turning. In this case, to the right is the direction of the center of the curve the car is turning. What force is making the car go to the right? Well, the car is only in contact with the road, so the road must be pushing on the car to the right. The road pushing is the force of friction. A level curve on a country road has a radius of 150 meters. What is the maximum speed at which this curve can be safely negotiated on a rainy day when the coefficient of friction between the tires on a car on the road is just 0.40? Well, if our net force is equal to the force of friction, Then our net force is related to an object going around a curve, so the net force is mv squared over r. And the net force is equal to the friction force, which is mu times the normal, which is mu times mg. Thus, mv squared over r is equal to mu times m times g. Canceling out the masses, we can solve for the velocities or the radii or whatever is particularly being asked. In this case, we are given the coefficient of friction. The masses cancel out, so all cars will make this turn at the same speed. Given the radius, what speed will the car need to make this turn? We can just plug in the given values. Banking is when a car is on not a level horizontal surface, but an angled surface, an incline, such as a racing car going around a track that's banked quite a lot. It's at a steep incline. The radius of the curve is pointing towards the center of the curve, but the normal force in this case is not perpendicular to the radius. The normal force is pointing at an angle. The normal force perpendicular to the surface, since the surface is inclined, the normal force has a component. The normal force is partly pointing in the direction of the center of the curve. So the normal force, the push of the road perpendicular, has a component, a push partly towards the center of the curve. The net force is made up of both the friction and the normal force. So the net force, the force needed for the car to make this turn, has contributions from the surface of the road, both from the friction and the normal force. So cars take banked roads when they go fast because the road can contribute both its normal force and its friction to making a car go fast around a curve. So racing cars will go around banked curves because both friction and the normal force can contribute to a greater net force for greater speeds. Airplanes also take an incline or a banked motion when they take a curve. So both the weight and friction can contribute to objects going faster when an object takes a banked position. Here we see these spaceships taking a banked motion as they are taking a curve. Hollywood usually gets this wrong because when airplanes bend their wings to take an incline to make a curve, it's the force of the air, not the force of the road, that pushes on the airplanes to make them bank. But a spaceship is in space. There is no air. So there is no force of air to help a spaceship make a bank. So this would simply be impossible. Another extension of the idea of non-uniform motion is to take an object that's going in non-uniform motion and fling it, to release the golf club, in a sense, from the beginning example. Here, let's look at a catapult. A 10-meter catapult is set to fling a cow at an initial angle to the ground of 0 degrees. Here's our cow being flung along a 10-meter lever from initial angle theta of 10 degrees. The catapult flings the cow. The catapult rises to 90 degrees from the ground. After 2 seconds, it will release the cow in this swinging. And now the cow is catapulted. We can calculate the initial speed of the cow after it's been catapulted. If at the launching position the cow is 11 meters off the ground, how far will the cow fly? Well, the cow is going through non-uniform circular motion, just as our previous examples. We can figure out the cow's velocity, its tangential velocity as it leaves, by knowing its angular velocity, omega, after we figure out the angular acceleration as this cow is being moved through non-uniform motion. So the velocity, the tangential velocity, relates to the radius of the curve, in this case 10 meters, the length of the lever that the cow is on from the pivot position, times it by r, the radius, times it by the angular velocity omega, which was 10 degrees to 90 degrees in 2 seconds. Omega final versus omega initial, plus the angular acceleration over time, one of our kinematic equations except the angular form of it. We know the time. Omega initial is 0, so omega final is simply a times t, alpha times t. the change in angle is going from 10 degrees to 90 degrees. Omega initial times t, again, is a term that goes to 0. Since omega initial is 0, the cow starts at rest. If we know alpha, or given the time, we can figure out the change in angle. But we know the change in angle is 10 to 90. So the change in angle is 80 degrees. We express this in radians. Knowing the time is 2 seconds, we can solve for alpha. Solving for alpha, given the angle that the cow swept and the time, we can plug it back into our original equation. Omega final equals alpha times t, all known quantities. Now that we know the final omega, we know the final tangential velocity that the cow has when it leaves, or any object leaves when it's being catapulted or flung. Thus we have calculated the final speed of the cow as it's being launched from this catapult.